Hey, this is just a quick note about our sponsor, Privado, the premier enterprise privacy platform, purpose-built to bridge the gap between privacy and engineering. Its privacy code scanning solution embeds privacy compliance and governance into the product development lifecycle and empowers privacy and security teams with unparalleled visibility of sensitive data flows and the insights to find and fix privacy vulnerabilities. You can leverage Privado's data flows, dynamic data mapping, privacy assessment automation, and real-time visibility of privacy issues. Enter the era of proactive privacy and transform privacy from business blocker to business enabler. To learn more, go to privado.ai. Hello, I am Deborah J. Farber. Welcome to the Shifting Privacy Left podcast, where we talk about embedding privacy by design and default into the engineering function to prevent privacy harms to humans and to prevent dystopia. Each week, we'll bring you unique discussions with global privacy technologists and innovators working at the bleeding edge of privacy research and emerging technologies, standards, business models, and ecosystems. Today, I'm delighted to welcome my next guest, Kurt R. Rohloff, CTO and co-founder of Duality Technologies, a privacy tech company that enables organizations and regulated industries to leverage data across their ecosystem to generate joint insights for better business while preserving privacy. Kurt has an impressive list of accomplishments. He co-founded the open source Open FHE Homomorphic Encryption software library that enables practical and usable privacy and collaborative data analytics. He's successfully led teams that are developing, transitioning, and applying first in the world new technology capabilities for both the Department of Defense and commercial use. And he specializes in generating, developing, and commercializing innovative, secure computing technologies with a focus on privacy and AI ML at scale. Today, we'll be discussing the use cases for leveraging homomorphic encryption and other PETs. Welcome, Kurt.
Hi, Deborah. Thank you for inviting me. I'm very happy to be here.
Excellent. I'm really excited. Last week, we learned a little bit about federated learning. And this week, I know we're going to be learning more about maybe how you could do secure federated learning using homomorphic encryption and, a few other really interesting applications. So I want to set up the problems that homomorphic encryption solves for as a PET before we dive into what it is and how and when we deploy it. So in most organizations, data remains largely underutilized, often restricted by privacy concerns, and a major conflict remains between gaining utility from a data set and protecting the privacy of the individuals or entities. So first question to you, what approach can companies take to overcome this challenge?
Sure, that's a great question. We see very regularly that large organizations, whether it's governments or companies or other kinds of entities, are typically sitting on piles and piles of data, typically, in different silos. And there's a lot of value for whether it's different departments in a company to be able to collaborate in ways they previously haven't been able to, or, for example, different companies or public-private partnerships between companies and government to collaborate on data to unlock value. And there's, of course, I don't think I need to convince you. There's plenty of use cases for these, and I'm happy to dig into a few of them. And I think you hit the nail on the head overall, that there historically has been a big trade-off between the use of data versus privacy associated with data, where either data needs to be shared in the clear historically or not shared at all, and all the protections have been primarily legal, protection through NDAs, data use agreements, things like that, where lawyers typically need to get involved to write rather sometimes onerous and heavy agreements overall. And as I'm sure you and your audience is aware, there's been an explosion of various kinds of privacy technologies over the past days, weeks, years, decades to help to solve this problem overall. I've been particularly working on a set of use cases that are addressed with a technology called homomorphic encryption, also called fully homomorphic encryption, where the base capability is to take data, encrypt it, And then this data, well, if it's encrypted with these fully homomorphic encryption techniques, also called FHE, can then be computed on while it's encrypted and further processed. And FHE is one of the really nice things about it, as opposed to other kinds of privacy technologies, is that it is quite general and quite malleable, where you can often take data sets from multiple sources, encrypt it with different keys, and still run on joint computations on this data, distribute the computations, distribute the data, and have all different kinds of interaction models and different kinds of computations that could be supported overall. And so to kind of put a finer point on it, one of the reasons I've really focused, this phase of my career and Duality as Technologies as a startup on fully homomorphic encryption is this very kind of general sets of functionalities, very malleable sets of functionalities enabled by FHE or fully homomorphic encryption. So I'll pause there.
Awesome. No, thank you for that. I appreciate it. So since each organization has different needs when it comes to data collaboration, looks like Duality offers the 3 separate models for collaboration, enabling an organization to, secure sensitive data while still allowing different types of sharing. And you list these 3 separate models on your website. So how about I list each one out and then you tell us a little more about it. The first one is analytics of a single data set. When would you use that model?
Sure thing. There's a couple different use cases for this. This is what in this privacy space we often call about the move to cloud type use case, where an organization might be running their own server, and they run their own server specifically so they could have a high degree of control and protection over a set of data, but they don't necessarily want to have the cost associated with running their own server, or even the liability associated with if the server goes down, do they have adequate backups, all these other kinds of more pragmatic issues associated with running one's own set of services. And so an organization would want to move their data set from on-prem to a cloud environment and obtain the associated cost reductions with that. And so that's, in some sense, kind of the canonical model that's been used for fully homomorphic encryption, is to take data, encrypt it, throw it up on some sort of cloud service, and then use the magic of the homomorphic encryption to maintain the same set of services, computation capabilities, and analytics on this data set as what had been run for the data when it was on-prem and not encrypted.
Great. And then the second model would be where there's analytics of a union of data sets that you refer to as horizontal data analysis.
Right. And we see this often in any number of use cases, domains, and I'm going to particularly look at the a set of medical domains. We were running a set of projects funded by the NIH, National Institute of Health, where they would want to take patient data to better analyze things called rare diseases. And so rare diseases are rather problematic in that, I think the formal definition, I could look it up, but it's something like, rare diseases affect something like 1 in 100,000 people over a given year. And so these kinds of diseases, a hospital might see, any kind of random hospital might see a specific kind of rare disease maybe once over the lifetime of the hospital, once every several decades. But the problem with these rare diseases is that if you look at all of the rare diseases over the entire population of the United States, or even the entire population of the world, rare diseases writ large are shockingly common, where it actually affects, multiple percentages of the entire population, whether, United States or world. And so the trouble with these rare diseases is that they might be eminently treatable if only researchers, clinicians, medical professionals could get adequately large data sets to treat these diseases.
And is that because the privacy challenge there is just even knowing that there is one disease at one hospital, that's just too much data points where you could track it back to, it wouldn't be anonymized. You could figure out who it is if there's only like one person in a geographical area with that particular disease. Is that what makes it much more difficult to do? Or is it that you need a lot more data about the general population to kind of filter out why they don't have the disease as well? Like, I'm just trying to understand that challenge there.
Yeah. No, great question. And the really pragmatic question that's been driving this from an NIH perspective is that in order to have an adequately large data set to see like what are symptoms, what are genetic mutations associated of leading indicators of a disease, is that they would need to basically join data across many different hospitals across the United States in order to have a hope of coming up with treatments for rare diseases. And so is that really the issue? Not so much the re-identification issue that you alluded to, but the issue of actually having adequate data to do any kind of reasonably scientifically accurate or scientifically trusted analysis of what are the correlations of mutations or otherwise associated with the prevalence of a certain kinds of disease to even hope to begin treatment studies as it is. And so this is, for example, joining data sets of patients over many hospitals, whether it's all the hospitals in a state or all the certain classes of hospitals across the country. And this combining of patient data across these many hospitals is what we call the horizontal join, for what it is, where you're basically, the simplistic version is aggregating data over many, many sources in a way such that no one individual at any one point is able to access the population of data, for example, across the United States.
Got it. That makes sense. And then it seems that that's where they share the same kind of data schema, right? In the horizontal data analysis.
Yeah, basically right. Where basically you think about a spreadsheet is basically you have all spreadsheets that have the same columns just over different people, and you're just adding more people to a spreadsheet overall.
Got it. Okay.
Yep.
And so then the third model is analytics of joined data sets, aka vertical data analysis.
Right. And this is a study that we did also for NIH in partnership with Dana-Farber Cancer Institute, Boston, and Harvard Medical School.
No relation to my last name.
Yeah. So for this use case in particular, you would have, for example, someone sequencing genetic data. A pile of patients would have the genetic data sequenced and just have it stored in some place like the Broad Institute or 23andMe or someplace like that. And then you would have a pile of clinical data. And this is data that doctors might take, like, blood test data and things like that. And if you have this data set from two different research centers with basically two different schemas, but there's commonality where there might be some patients that are in common between these two data sets, how do you join them in a way such that the patients that are common to both, their data basically lines up so you can start to adding columns to data as opposed to adding more rows to data. And this is also what we call the vertical join problem. And this is prevalent not just in medical, but also financial services and other kinds of related areas too. So, that has been kind of a very big growth area for us also.
Stay with us. We'll be right back.
Hello, loyal listeners. The Shifting Privacy Left podcast is seeking sponsors who want to help educate our growing community of privacy engineers. Position your brand in front of privacy engineers, architects, developers, researchers, and privacy tech buyers. Insert a 30 to 60 second ad like this one into every published episode of the podcast. This is dynamic content after all. Feature your new product, an upcoming conference, a sponsored special deal, endless opportunities. Email sponsorship@shiftingprivacyleft.com for more information on our sponsorship package. Okay, let's get back to our engaging privacy conversation. Awesome. So help me disambiguate in my mind. Last week we learned about federated learning and that you could have vertical federated learning as well as horizontal federated learning. And here I see the terms, vertical and horizontal data analysis. How would you compare the terminology? And does it have to do with the fact that it's on an encrypted data set, or is it something else?
That's an excellent question, Deborah. And there's a few aspects to this. And this gets a little bit more about why I'm particularly a fan of homomorphic encryption, which is basically that the homomorphic encryption techniques do allow these kinds of analysis that I outline. They also allow functionality for even training of machine learning models and things like that. And the generality also comes where the actual training and analysis computation, I've outlined a model where data is aggregated from multiple sources, and the aggregation could happen with a couple different security models. It could happen that the data is aggregated where all the data is encrypted with the same key. It could happen that the data is aggregated where each data set is encrypted with different keys. And so, for example, Harvard Medical School could have one data set that they encrypted with their key and only they can decrypt. And Broad Institute or Dana-Farber could encrypt with their key set and only they can decrypt that data. But these two encrypted data sets could be joined together and then computed upon also. And so it allows this kind of very fine-grained set of guarantees that that data can't migrate from Dana-Farber to Harvard Medical and vice versa. And the computation doesn't have to be at a single point. The computation could be distributed across various nodes, for example, some at Dana-Farber, some at Harvard Medical School. And it gets very confusing because in some sense, all the various options that we present for computation models that allows this really broad sense of generality for what it is in terms of how homomorphic encryption goes beyond some of the limitations of other kinds of PETS operations like federated learning. And of course, there's trade-offs, and I'm happy to talk about those too.
Yeah, that was my next question. I would assume the trade-off is the type of data that you're able to extract or compute. Am I correct in that assumption? And then when would you, besides the access control aspect of like who has the key and who has access to the raw data, why would you use secure federated learning on encrypted data rather than typical federated learning? Like why use fully homomorphic encryption? And the second part of that is, if you're using it, what are the trade-offs?
So one of the things that the bit of a truism is life is that there's no free lunch. And as I also like to say, is kind of like, a privacy technologist is like a cook. When you want to cook a meal, you use whatever tool you have in the kitchen to get it done. And the trade-offs between federated learning versus homomorphic encryption is, yes, homomorphic encryption has all these nice generality properties to it that you can, in theory, support general computation. Homomorphic crypto is quite good when you're dealing with highly structured tabular data, network, the kind of things that you could put into a spreadsheet and compute on, over things that look like matrices and things like this. The other side of it is that federated learning type techniques, they don't quite have the generality of homomorphic encryption, but what they do well, they do relatively quickly as compared to homomorphic encryption. So, and this is something that's known about homomorphic encryption, in the broad, is that there are slowdowns associated with it, and it can be computationally very heavy. I don't think it's anywhere near as bad as it definitely used to be, and I can talk definitely about the history of where it is and where it's been, where it's going. But like I said, it does come with its own computational workloads, but you do also get these extremely high levels of security with these cryptographic mathematical guarantees, and it's even what we call post-quantum, meaning resistant to quantum computing attacks. So very, very, very high degrees of security and generality associated with it, but of course it comes with the cost of computational load and speed and things like that.
That makes sense. I would love to hear, how it started and how it's going, because the last I had really dived deep into this space, specifically around homomorphic encryption, it's been a while, and it was generally thought of as really great in the lab, but maybe not ready for prime time. I know it's a few years ago, so like I'm not talking about last month or anything.
Sure.
So yeah, I'd love to understand your perspective.
Yeah, no. So I've been supporting homomorphic encryption since it was really first discovered, and I got involved. One of the seminal projects for this was a project that DARPA funded that I was running one of the implementation teams for DARPA called Proceed. And, when this first happened, the very, very first implementation of homomorphic encryption that I'm aware of was done by two gentlemen, phenomenal researchers by the names of Craig Gentry and Shai Halevi. And their first implementation of fully homomorphic encryption, they took basically 2 bits, encrypted 2 bits, and then ran a bitwise AND operation in a special operation called bootstrapping. And just this encrypted bitwise AND operation with bootstrapping took an entire half hour of wall clock time, which is just crazy, computational load. And what Proceed did, this DARPA program, was really to focus on accelerating that by many orders of magnitude. And over the course of 4 years in this DARPA Proceed program, where a lot of the real seminal work in homomorphic encryption was done, both in theory, design, implementation, and so forth, we improved performance over 4 years by 6 orders of magnitude. So that's a million times faster over the course of 4 years. So faster than Moore's law performance improvement. And at the end of the program, we were able to deploy what was then the cutting edge of homomorphic encryption on stock iPhone 5Ss. So 2013 timeframe, exactly 10 years ago. And what we were able to do was to run encrypted voice over IP operations. We were able to encrypt audio conversations like the one you or I are having right now on these stock iPhone 5Ss, and then start doing teleconferencing with audio quality comparable to what we're hearing right now on this call back in 2013 with homomorphic encryption, which is just, first off, I think it's a wonderful data point of how, homomorphic encryption has a slowdown, but it's really pretty darn good to be able to do voice over IP on commercial data networks with no real perceptible lag, at least to a human ear. And that, like I said, was 10 years ago. Since then, it's been leaps and bounds where we, about 4 or 5 years ago, we did the study for NIH where we were basically taking real world workloads from Dana-Farber Cancer Institute, and we're running these operations for things like chi-squared analytics and whatnot, which are, computations actually used for genome-wide association studies and running in the order of seconds and things like that. And we're currently in this commercial sets of activities that we're doing at Duality, where we can start to doing things like running encrypted queries on data with responses of running hundreds of queries and responses on the order of seconds and things like this. And there's even the future beyond this, which is to we're currently working on a project for the DoD that is running convolutional neural net training, training of neural nets on encrypted imagery data. And the vision is that we're going to be running at line speed with no slowdown at all on encrypted imagery data.
Wow.
So we've gone like tremendously faster, and there's a heck of a lot left to go. That's really just in the making right now.
That's fascinating. And what determines increasing the speed? I mean, is it a matter of hardware or is it software?
It's a little bit of everything. A lot of it came from just better crypto protocols, better math. A lot of it came from a lot of homomorphic encryption. It's an encryption scheme, which means you have to generate a lot of high entropy noise, a lot of random numbers. And we figure special kinds of random numbers with kind of unusual distributions. And we figured out how to implement random number generation for this special kind of random numbers very, very, very quickly. And that was huge for us. And then there's a lot of software of algorithm design of how to parallelize. And the other side is understanding the workloads better. One thing that's really interesting about homomorphic encryption and about privacy technologies in general is they're basically like a fancy compute engine where homomorphic encryption has an instruction set, similar to the instruction set that you would have for like an Intel chip or something like that. But the instruction set is kind of unusual. It's something that looks like a vectorized addition and something that kind of looks like a vectorized convolution. And you need to use these unusual operations to do all different operations that I talked about, like neural net training, logistic regression, chi-squared analytics, and so forth. And so the mapping of how one takes existing workloads and puts that into things that would run on homomorphic encryption has been a huge deal overall. And understanding how to do that much, much better has been a huge push in further performance improvements associated with applied homomorphic encryption and how we just optimize workloads that run on top of FHE.
Wow. Yeah. And I appreciate the detailed answer because I know there's plenty of listeners who are going, you're scratching their itch for information at a technical level. So let's dive into some of the use cases for homomorphic encryption. I know that at Duality, you focus on organizations that are highly regulated. And honestly, as a initial sector to go after. That's a pretty common one for enterprise. And I think it makes a lot of sense since there's such a great need there. And I know you mentioned a little bit about, healthcare use case before. I'm going to list out some of the use case categories, and I'd love for you to expound upon each one if that's possible.
Yeah, happy to. Sure.
Okay. So first, let's start with financial services. You say that it helps with fraud prevention, anti-money laundering, and trade financing. So how about let's start with fraud prevention? Is it homomorphic encryption by itself or in combination with some other PETs?
Fraud is a many-headed beast, and there's all different kinds of fraud, and there's all different kinds of fraudsters, criminals that perform, fraudulent activities. Kind of the very simplistic one is basically scammers who will basically might send you email or text message or things like that, the proverbial Nigerian prince. Typically, these scammers, they don't go after just one individual. They go after many different individuals to try to victimize them. And typically that, in order to kind of get around financial reporting laws, they maintain many bank accounts across many banks, sometimes all the same address, sometimes all with the same phone number. And they really know no geographic boundaries for what it is. And so what will happen is that these fraudsters will typically, take money from someone, the proverbial, grandmother sitting at home and getting, scammed by someone. And as financial crime investigators, whether it's within a bank or at a credit card company or in law enforcement, will want to ask the banks information about where these accounts are based, what addresses are associated with them, what phone numbers, and even a little bit beyond that, of how many accounts are at this address, how many accounts are affiliated with a certain kind of phone number. And so typically what happens is that when a law enforcement or fraud investigator or something like that, wants to run these investigations, at least at banks, will span multiple banks. And so the banks might coordinate to perform these investigations, both to fight fraud and also to reduce their financial losses to scammers. And so they want to collaborate on these kinds of things, but don't necessarily want to reveal customer information, legit customer information to their notional competitors. So what will happen is that a fraud investigator at a bank might run queries to colleagues at other banks to say, hey, do you have any accounts at this address, or do you have any accounts at that address? Then without wanting to reveal any information about legit accounts. And so we have a set of capabilities that's used in financial services and to fight, financial crime in general, that allows a fraud investigator to take a query, query about an address, a name, a phone number, things like that, encrypt that query, send the encrypted query off to potentially to a competing bank or even a different division in a bank. And I'll get into that in a little bit. And then, get back results without revealing to the other bank or the division what the subject of investigation is. And then, if they get sufficient hits, then they have evidence to start, operating in the clear and coordinating in the clear with other banks, other divisions to do basically debank, to remove the scam accounts from their books and reduce the ability of the scammers to perpetrate their crimes.
Awesome. And so then the next category is government. I assumed that there'd be like a large number of use cases that you'd be working towards, but here you have secure investigations. So is it that that's such a large area that the government is just, prioritizing over others? Or is that really just, kind of the best use case for fully homomorphic encryption?
It's a great early use case.
So there's probably going to be more.
Oh, yeah.
Oh, okay.
There are. I'm very proud that the work that the team has been doing for DoD and DARPA over the years, and there has been a number of government kind of motivations associated with this, including moving to the cloud and coordination across government entities to have better, for example, policy positions and grant making activities. Census Bureau rather famously has started using privacy technologies and things like that for privacy protected analytics and things like this. But, fraud analytics has been a pretty big deal for us overall associated with secure investigations. And there's actually like a big financial motivation, like a tax efficiency kind of motivation for this, where, right now, if federal law enforcement or just law enforcement in general wants to run an investigation, typically they will have to go and get, something like a warrant from a judge to run an investigation. And this will often take, days, weeks, months, because there's some of the privacy implications associated with asking questions about, certain addresses and what information that might reveal and things like this. So what we can enable law enforcement to do is to reduce the legal burden associated with asking banks information, so that they can basically move much more quickly and more cost effectively. So they don't necessarily have to involve as many lawyers. They don't have to necessarily spend as much time in front of a judge. And also for a high degree of really operational security, where when they run and send a query over to a bank, if there were organized crime insiders within a bank, the organized crime insiders won't necessarily get tipped off about what law enforcement is trying to ask about, so that both the law enforcement can move more quickly and more stealthily against financial crime perpetrators. And so this has been, a big win-win all the way around, in that, less tax money goes to being spent on these investigations. The investigations move much, much more quickly, and the investigations are at much less risk of tipping off organized crime about the existence of these investigations also. So, there's a multitude of benefits for using privacy technologies in these ways.
That's fascinating. And I think everybody loves when the government is saving our money. So,
yes.
As well as de-risking and respecting privacy. So huge win. And then the third category and use cases that you've deployed of these technologies is you have as real world evidence. And then I think we talked a little bit about healthcare before, but maybe in this context is more specific, genome-wide association studies.
Right. Real world evidence, also called RWE, is kind of a really interesting one. And this also gets again to things like governmental efficiency and things like this. So what happens is that when the FDA wants to approve a medication for use, they have the best interest of our citizens at heart, and they really only want to approve medications for public use if and only if it's been shown to be safe and effective for the broad population. And so what happens is that pharmaceutical companies and otherwise spend a tremendous amount of time basically gathering evidence associated with the effectiveness and safety of medications. And so this results in the aggregation of a lot of really sensitive medical information, a lot of really sensitive demographic information also about individuals. And it's no secret that often that once a medicine is approved, it's sometimes later found to potentially be effective for other kinds of diseases. And we'll see this often, with where there was a lot of trial and error associated with to see what kind of medications in the early days of the pandemic might have been effective against COVID-19, for example. But what happens is that, like I said, these processes are extremely time consuming because they have to, so much data has to be collected. And so there's always been this really interesting question: how can data be reused? That if data is, for example, has been used to prove the efficacy and safety of a heart medication, can we also test if the same medication might be useful for some generic, dermatological disorder or something like this? And rather than going and generating new data associated with people that might have a certain skin condition, we can start to reuse the data using this notion of real world evidence in a privacy protected manner to develop treatments for, say, a skin condition and things like this much, much more quickly, and get an effective medication out to market much more quickly for the betterment and well-being and health of our fellow citizens.
That's compelling, especially as I'm dealing with an eczema flare-up as we speak. Yeah, I know, probably TMI, but I just think it's relevant. I don't think this is going into any random database right now. But that's really compelling examples. And so it makes me wonder, are you seeing like a proliferation of standards all over the place to, in each of these verticals, like financial services within the government, NIST, healthcare space? Like, are there standards being developed so that there's a systemized way and a best practice of deploying these technologies?
Yeah, there has been. There actually has been quite a bit of movement lately. One thing that's really interesting about standards is first off, I'm going to say things that might seem kind of obvious when I say them, but sometimes they're epiphanies for engineers that are kind of like down in the thick of things. Standards are really about how to enable interoperability and trust in technologies and that things will work and whatnot. And this is especially important for privacy technologies because you think about privacy technologies inherently are supposed to secure sensitive information. And so if you want to secure sensitive information, the best way you can do that is to use trusted technologies that have been vetted, whether it's through academic peer review or government review or whatnot. And there's the kind of three aspects of that. Like for one, we at Duality, we only use encryption protocols that have gone through very intense peer review and gone through the academic publishing process. We only use open source implementations of cryptography, and we only use security settings of the cryptography that have been vetted and moved into international standards. And these three things are just so fundamentally critical for trust and privacy of operations on very, very sensitive data. And the other side of it, of course, as I say, is interoperability. The notion of using privacy technologies is really about sharing and collaborating on data in some sort of fundamental way, which leads directly in a kind of like a bright flashing line to interoperability. And of course, the need for standards for interoperability also. So there's been a number of rather, very healthy standardization processes that have been ongoing. Probably the earliest one for homomorphic encryption has been an organization called homomorphicencryption.org, which we co-founded with the teams from IBM and Intel and Microsoft that has since grown. And we have a standards meeting every 6 months or so. And our next one's actually going to be in March in Seoul, South Korea, hosted by Samsung and Seoul National University. And it's been a very, very healthy activity with participation from large industry, from startups, from government, and so forth. And that really sparked a number of other efforts where there's been an engaging interest from NIST, and NIST, as part of the Department of Commerce in the United States, is the national standards body for the United States. And they really only get involved in standardization processes.
Sorry to interrupt. So when you say the United States, what we're talking about is for the U.S. agencies that the U.S. government oversees. Just wanted to make that clear to the audience.
Yes and no, actually. I'll come back to that actually in a little second. You actually make a really nice point that's a little subtle about that, but I'll come back to that in a second.
Okay, great.
But, also there's been a push in ISO, in IETF, in ITU, which are three major standards organizations that do drive international standards associated with privacy, security, and other kinds of things. And there was recently a draft ISO standard specifically for fully homomorphic encryption that came out of the homomorphicencryption.org activities. So, really great stuff because there are these international standards bodies. To come back to NIST, and I think this is great that you asked about this. NIST is National Institute of Standards and Technology. It's a component part of Department of Commerce in the United States. NIST basically defines the public standards for cryptographic protocols, notionally for U.S. government, but it's basically NIST standards drive, for lack of a better term, world commerce. That NIST standards are basically taken as the gold standard internationally. They're taken the gold standard for, even areas that they don't necessarily have a regulatory domain over. And so NIST being kind of perceived as the end all be all of standards for highly, highly, highly trusted technologies. And they've recently put out things like post-quantum crypto standards and things like that, and have basically started the process of engaging in privacy technologies such as homomorphic encryption and secure multi-party and zero knowledge proofs and a few other things related to that also, which is great because, once NIST gets involved, it means basically they only get involved if they think that there is real commerce behind something. And so it's a great indicator that the market is really picking up when an organization as big and as heavy as NIST really takes close attention to something.
Absolutely. And you also make a great distinction there with a difference that is important, that they are not just the standards org, they are, setting the standard and a best practice that is picked up not only in the US, but can be globally as a standard to build towards. I guess what I was trying to get at is that it is almost like the internal policy for all the departments and agencies within those departments, that when NIST puts a standard in place, they're compelled to follow those standards as if it's their company mandate. Whereas it could be put in contract with someone who's doing business with the government, that you have to comply with them, or it could be put in private sector contracts that someone's conforming to NIST standards, but it's not like a force of law, the requirement for the most part. And I guess that was the distinction I was trying to make. But you make an excellent point too.
Right. No, point very well taken. That NIST, in some sense, I think I forget the exact terminology that they use, but what's coming to mind, is that it's not so much NIST standards always; they're often NIST recommendations, like for privacy frameworks and things like that. So you make an excellent point in those regards. And thank you.
Yes, in fact, at one point there was more of I forget what it was, but when they came out with their guidance on privacy engineering, but it ended up being more of a guide to, as opposed to a requirement style like framework, risk framework. And that it seemed almost like the initial body of knowledge as they were building towards embedding those concepts and evolving what privacy engineering means into, future frameworks and standards.
For sure. No, for sure.
So you're right. There's always these different things they put out that have different forces of law, so to speak. Great. Well, so just two more questions for you. I mean, the first is I'd love to know about Open FHE and just a little more as to who led the efforts to build it, for what purpose, and then, what are the benefits of others using Open FHE?
So Open FHE, find the website openfhe.org, is really the leading open source library for implementations of fully homomorphic encryption protocols. It's a project that I've been involved with for the past decade, and I was one of the co-founding people behind it, including my longtime research collaborator, research partner, Yuri Polyakov and David Cousins and several others. And it really grew out actually spiritually and actually practically out of this very early DARPA Proceed program I referred to earlier. I've been very fortunate that, and I think it's actually very, very fortunate for us in general, that DoD and DARPA in particular has been very interested in the propagation of privacy technologies. And there's been a series of DARPA-funded efforts that has led to increasingly higher quality implementations of, and higher performance and higher capable implementations of fully homomorphic encryption. Library was something that was called Palisade that we worked on for many years. A year or two ago, we decided to basically re-engineer what was Palisade, which was also a homomorphic encryption library, an open source one. And with collaboration with the team from Intel and the team from Samsung, and also some participation from MIT and a few others, we rebuilt the Palisade into OpenFHE as an open framework that supports all of the major fully homomorphic encryption protocols. It's really intended to be a production-ready implementation of fully homomorphic encryption. One of the troubles with a lot of the prior open source implementations, and still actually, the vast majority of current open source homomorphic encryption implementations, is that the libraries are really more research projects, driven by the intent to kind of write a few papers and something like that. Not really hardened production-ready libraries. And what we want to do with Palisade and OpenFHE, particularly with a lot of this, very generous support we've been getting from our sponsors, is to build an open source library that is production ready, that is performant, that is ready for use. And in some sense, I say this somewhat tongue in cheek, to be as boring as possible because it just works. And so OpenFHE is the genesis of that, or is the result of that, excuse me, for a general set of fully homomorphic encryption implementations that are standards compliant, that can be tied in with hardware accelerators, that have general high-level SDKs that conform to standards, so that they're basically just easy to use and drop in for use cases as much as possible for privacy technologies.
That's pretty awesome. What other resources would you recommend to privacy technologists and data scientists who want to learn more about this space and, any training or fellowship opportunities or upcoming conferences or community groups to plug into?
There's a lot. This is one thing that's actually kind of fun about the privacy community in general, is there's a lot of stuff going on, and there's different ways of getting into the community. I'm very much in the applied space, for example, implementing privacy technologies and applying privacy technologies. And there are any number of open source projects that exist for this. There's all kinds of open source projects for, like, secure multi-party and federated learning. OpenFHE is, of course, a big one for homomorphic encryption. And then there's also work on libraries that layer on top of libraries like OpenFHE for, the integration of these capabilities. And so, for example, Google recently put out what they call a transpiler, which takes C++ programs and compiles them to circuits that run on top of OpenFHE. And this has been a real fun project for us to collaborate on with Google too. There's piles of academic work in the space associated with writing papers associated with cryptography. And my partner, co-founder, Vinod Vaikunathan and Shafi Goldwasser at MIT and Berkeley, respectively, have been very big in the space. And, if you want to work in academic cryptography, math is a huge deal for that. I'm more of a systems person. And so my background is more in engineering and getting things built and making things run fast. And so, experience with embedded systems is a huge deal for actually applied cryptography and implementing that stuff. And then even at the application layer for the formulation of privacy tools from privacy technologies, there are plenty of events like that, like the PETS conferences and whatnot. One that's very near and dear to my heart is a workshop called WAHC, Workshop on Applied Homomorphic Cryptography, that I've been running with friends and colleagues for the past, I think 10 years now, give or take. And we're always affiliated with or an academic conference called CCS, which is one of the leading cybersecurity conferences. So that's a big one that always has a lot of good papers and things like that too. Admittedly, more on the academic side but we do talk quite a bit about implementations and software and how software privacy should and could work.
That's awesome. That's actually like a more full answer than I was expecting, which I think is going to be helpful to, how do you plug into this space? Like, how do you maybe even change careers from one focus on, within privacy to another? And you listed some really great entry points. So thank you for that. And thank you for your time today. This has really been a fascinating conversation.
Deborah, thank you very much. This has been a very fun conversation. And one of the nice things about having an unusual name like I do is I'm very easy to find online. And if any of your listeners want to reach out, happy to chat.
That is right. And I will put your contact information in the show notes, along with some of the many resources you listed. There's only so much space that they give me in the platform, but there's so much information here. So I'll also say that in the transcript, I'll have hyperlinks to definitely all of the resources that are stated here to make sure everyone, can easily find it. Thank you, Kurt.
Thank you.
We'll be back with engaging content and another great guest. Thanks for joining us this week on Shifting Privacy Left. Make sure to visit our website, shiftingprivacyleft.com, where you can subscribe to updates so you'll never miss a show. While you're at it, if you found this episode valuable, go ahead and share it with a friend. And if you're an engineer who cares passionately about privacy, check out Privado, the developer-friendly privacy platform and sponsor of this show. To learn more, go to privado.ai. Be sure to tune in next Tuesday for a new episode. Bye for now.